Alright, so today, day 47, what I did was mostly focusing on robust optimization. I finished, we were seeing yesterday the Vertsimas like framework for understanding like robust optimization. Essentially, in robust optimization, we have an optimization problem. Normally, the main intuition, like the added layer, is that now the coefficients of a particular constraint could be uncertain. So you have a set. And what we do is that we assume that the worst case scenario is going to happen to all variables at the same time. And we solve for this problem. And that's called Soister's approach. All right. And then there is this new framework, which is the Vertsimasim model, in which we can select how many worst case parameters are we going to have, and that's essentially it. And the way to do it is that the main intuition is that we enforce another maximization problem inside our maximization problem. So given a problem that it could be, I don't know, that it's like this one, right? You have to imagine this is a matrix. This is a vector of uncertain coefficients. This is only the constraints, right? And what we're saying here is that the coefficient aj, it's a set, right? And we can like express this coefficient as a sum of a nominal value plus like some epsilon, like some deviation from the nominal value. And this epsilon is like between -1 and 1 because it's like upper and lower bound times some scaling, which is this aj hat, right? And basically we define the uncertainty in this way. Then given this way of defining uncertainty, we say that we want we can express it as a function. He uses, I think, the beta function that takes gamma as a parameter. Yeah, so basically this is the same as before, and we can express this as this is the original constraint. We can express it more robust in this way because we want to take the worst case scenario in as many as gamma parameters. So we are taking the maximum value that it could take for each parameter gamma. So we don't know, essentially it's like we don't know which value it's going to be the worst, but we have to take the worst. I don't know. Okay, one way to think about it is like you have 10 possible values, 5 are going to be the worst, so you have to be sure that in the worst 5 scenarios it's gonna be still feasible. It's gonna still be the solution feasible, because being feasible for the 5 worst means that you are feasible for any 5. Does it make sense? And that's actually what this framework does. You are being feasible for any gamma by being feasible for the worst gamma, right? That's essentially it. And then you can apply this it's very interesting because given this formulation you have like a optimization problem inside the constraint, and you can express it as a dual problem. So you will have a minimization problem, and this minimization problem can be substituted in the original constraint, so it can be expressed as directly as one big optimization problem. That's basically the intuition. I'm gonna show just the final form. Yeah, this is the final form. So we're gonna have this the same the constraint. Instead of being like the previous one, we're gonna have this, right? We're gonna have these two added parameters, which is zeta 0 and pj, that are like a consequence of solving a minimization problem using like the dual interpretation of the of the robust optimization. That's it. I think today I'm not being that concrete, but I don't want to spend too much time on this. I just want to give a quick recap. And what other interesting thing is this one, that you can compute like a guarantee, which is like the probability of a constraint violation is going to be less or equal that e to the minus lambda square over 2n. So you can have like a statistical kind of guarantee for robust optimization. And then there is stochastic programming, which is also very interesting. Okay, but that's like this about robust optimization. Then I also checked a couple of things about column generation and constraint generation. I also implemented some code. Well, I didn't implement it because I did it before, but I read it again about the cutting stock problem, which is this one, in which essentially there are like two main formulations for the cutting stock. The first one is like the ILP formulation, and in the integer linear programming formulation, you have to, in the cutting stock, it's like you have a roll and you have to get items, and to get the items you have to cut the roll, and you want to minimize the amount of rolls used. That's essentially it. And depending on how you say that you are going to solve the problem, it's like the complexity it takes. For example, this one is just like by enumeration. So you enumerate all rows that you have and you select like a big number, and then you have like a matrix that tells you like this pattern, this row, no patterns yet. It's just this item, it's used this many times in this row. That's it. And you do it like for all rows and so on. You solve the problem. That's it. There is also the column generation, in which this one is the interesting one. In this problem, instead of solving, what you do is you use patterns. So you say, I can cut the row in this pattern, right? But the thing is, like, we have like many patterns, like there could be exponential patterns. So the smart thing about this algorithm is not solving like the formulation in the pattern way, in the pattern based, but rather solving like a smaller version of it, and then adding like a pattern that maximizes, that improves, it's called improves the reduced cost. So basically you solve it for a smaller instance of the problem, and define like a pricing problem, solve the pricing problem, and add a column, and you can have a better instance of the problem, and so on, and you repeat this over and over again. Then if you compare the complexity time, essentially the standard ILP it's exponential. I had to cut it off because it took like 2 hours and it didn't finish running. Alright, and what else? There are many things that are interesting. I might cover a couple of them later, but I don't have enough time. I gotta go to sleep now.